Hey everyone, I am Saheb Kumar and welcome to PrepTrain, another video of Break the Tech series. For the past week, I have been going through this research paper from Facebook on design of one of their large scale caching system, which is basically scaling Memcached at Facebook. And believe me, I don't know if you are watching this video in late 2025, 2026, or maybe 5 years from now on, it does not matter. This one single research paper can help you understand caching at a depth that no other 10 to 15 minutes of what is cache video on YouTube ever will. To give you some context, Memcached itself started around 2003, and this paper was published a full decade later, like in 2013, at some NSDI conference. And it's not about the invention of Memcached; it's more about its evolution. So it is the story of how Facebook engineers took this very simple, lovely open source tool and spent years transforming it into one of the largest, most critical distributed systems on the planet in terms of caching. And we are talking about a system that at the time of writing of this research paper was handling billions of requests per second and storing trillions of items, which is mentioned inside this research paper. And the lessons that are inside of this research paper are on managing latency, load, and features at a scale are timeless. So today we are going to deep dive into this research paper. We will go through this research paper slide by slide, break down every key concept that is mentioned inside this. And all right, let's get started with another video of Break the Tech series and dissect this research paper. All right, let's start with the discussion video on scaling Memcached at Facebook. Before starting this video, I would like to discuss few of the paper's keywords that I found very interesting. And if you get time after this video or you want to deep dive further into this, you can go and look into these topics. These keywords are scattered across the research paper, like fan out, data replication, fault tolerance. You might be knowing some of them, but still, there might be few that you don't know. So you can look about them further. In cast congestion, MC router is something which is internal. Sliding window algorithm is something that you must have read or learned about in college, and it is getting used in this paper. Poison's arrival, Little's law, stealth sets, thundering herd. This is a very famous problem that we backend engineers face. There is gutter concept. mcsqueal is something again internal. Cold clusters and hot cluster, likewise cold db, hot db, and likewise it's similar. Remote marker mechanism, this is also a very interesting concept. uh, Transient item cache, all to all communication pattern, and system v shared memory. This is related to operating system if you have like studied it, but still you can look into it. All right, let's start the video. So in this video, we are going to talk about how Facebook basically built the world largest Memcached installation as claimed in their paper at that point of time. They took a very simple open source tool, which is actually like a single server thing, and they built a distributed system on top of it. So that is also very interesting to see. They claim that at the writing of this research paper, they were handling billions of requests per second and trillions of items in memory. So that also we will discuss in detail in this video. Before we get into the complex architecture, let's begin with the fundamentals, like what is a cache, why we use cache, and what is memcached. So when we talk about cache, it is basically a very high speed in-memory data layer which is used to reduce latency and protect backend services. So sounds kind of bookish, but the thing is we often use cache to reduce the load on DB by storing the most frequent, let's say, keys or queries directly on the cache, and it's in memory, so it is very fast as compared to a traditional disk-based IO where you go to the disk, you ask the database that hey, this is my query, and then the disk will go, it will find out all the answer, and then it will return you the answer. That again takes time, and then you return the answer. So in cache it is very fast. You just go there, you give the query, and that answer is already there if it has been asked before, so you directly get the answer. So likewise, now why cache? So like I said, we use it for reducing latency. So suppose in-memory reads are in order of like much faster as compared to disk based IO. Another interesting thing that you must have noticed, that if here is my DB and this is cache, although size of cache is much smaller, so let's make DB bigger. So the thing is, whatever incoming requests are coming, so cache is able to protect the DB from same queries. So if for one queries I am able to get the answer from DB, I will just store it on cache. So if similar query is coming, it will directly get it from cache instead of going to the DB. So this way we will be able to reduce the load on DB. Now that explains the second point of reducing load. Now let's talk about why Memcached. So we are talking about a era of 2003 when like tech was just growing up. So people can say, hey, why don't they use Redis? The thing is, at that point of time, using Memcached was a better decision because it was famous at that point of time, and it was very simple. By simple, I mean that it's just a giant distributed in memory hash map. So like I said, it's just a hash map and it gives you just three functions: get, set, and delete. That's it. By get, you means you can send a get query. Hey, what is the value of this? If you have. By set, you can set the value of a query, and delete is likewise you can delete a value of a particular key. Now here is things get interesting because these are very simple operations, and when we say distributed, so there are multiple servers, all are dumb, like as in they don't know that there are other servers existing. So if they get a query and they don't have the answer, they will just say that I don't have the answer. They will not say that, hey, you go and check with the other server. They are that much dumb. It is simple to implement for a very generic use case, and also as it's a volatile memory. So if the cache server gets down, the entire memory, like the entire caching goes down, all the keys values are lost, and people are ready to accept this flaw because of its simplicity. So there is nothing like a failure mechanism in Memcached. You might be thinking that why don't people just put DB and cache together in one place, or like bundle it together? And it that is also very interesting. So see, if this is your DB, let's say, and it can handle, let's say, 100 queries max in a second. Now the thing is that if you have a cache that can handle, let's say, 50 queries, or let's say 500 queries, so if you know that you are going to get redundant queries again and again, you can just scale the caching depending upon your need, and accordingly you can also scale your DB. So there is this separation that I wanted to talk about, that both of them can be scaled independently if you are having them separate, and it helps you save cost instead of bundling them together, and then whenever you want to scale up, you can just scale whichever component you want to scale. So we have discussed that what caching is, and why someone might need caching. But now let's dive deeper into the Facebook problem. And scale is not the only issue that they must be facing, right? We also need to look at what kind of workload they are operating on, and how is the DB being used. Is it a read heavy system or is it a write heavy system? So obviously, social media platforms generally have more number of consumers than the number of creators. So mostly it's a read heavy system, and that too excessive. So when we say read heavy, so users basically consume order of magnitude more content than what they are creating, and this is a perfect workload for caching. Now in case of Facebook, the research paper mentions that the kind of data that they were giving, getting in the cache itself is not very similar. It is coming from multiple sources in multiple formats, MySQL, HDFS, backend services. So it's very difficult to do queries on going in DB for these as well. So they need a place to store it properly so it can be achieved. There might be there is one mention on, like, I will discuss it later, but just wanted to give you a glimpse that often there are machine learning models which are actually trying to run a very excessive query, very heavy query, which is, let's say, running for days, one day. So in that case, storing that result directly on cache makes more sense, so that if some other people come and run the same query, they can just get the answer directly instead of doing the process again. So let's talk about one more interesting challenge, which is the fan out challenge. So when if you have seen Facebook 2003, 2005, or 2010, or even now, a single page load, people were crazy at that point of time. So a single page load would call so many content from so many sources, and it used to call like at least around in the paper they have mentioned that a single page load takes around 1000 db queries, and it's impossible to serve that many queries of to across a vast multitude of users. So caching obviously is the solution that they can go for. So overall, the goal became that they need to design a caching system which can serve all these heterogeneous read heavy system data at a very low latency around the globe to their global user base. Given that Facebook is facing such a massive fan out problem, let's talk about how the memcache will actually be in place before DB gets called. So there is a pattern called as look aside caching. If you have studied about caching, there are various ways you can put cache behind the DB, in front of the DB, and likewise we can discuss more of it in another video, but let's just discuss this one, which is the look aside caching. So what actually happens? So let's first understand the read path. So let's say the server wanted to, or client wanted to get a value from a cache, but what happened that the value was not stored on the memcache server. So what will happen? So first of all, a web server here, it will just ask the query to memcache that, hey, I want to get this value for this key k. Okay. And memcache will say, hey, I don't have it. So then uh, web server will go and ask to the DB, because DB is the original source of truth. Now once it gets the data that, hey, this is the value that you wanted, web server will come and set the value of key to whatever answer it has received from the database. So next time when the same query comes, the web server will get it directly from Memcache. You understood it? Now let's discuss one more case. What will happen if we actually want to update the value? By updating a value, what I mean is, now server wants to update value of a key in the DB. So it will go to the DB and it will say, hey, the new value of this key is, let's say, this. DB will, let's say, ACK, and it changes the value. Now the web server will not go to the memcache and say that, hey, this is the newly updated value, update it in your memory. Instead, it will say to memcache that, hey, delete whatever value you have for this key from your cache. Now, this might sound interesting, that why are we doing this? And the answer is very simple. Delete is idempotent as an operation. What do you mean by this? So let's say if we were trying to just update it in cache, what if again some update came after the initial update request, and that also was served by DB, and before the first request could come to memcache, that request came to the actual cache and that changed the value, and later on this old request, the first request value to memcache came that, hey, update the value. So what you will see is there are numerous possibilities of race conditions that can be possible if we are trying to update the cache. But if we just say, hey, delete the value, so next time if a query actually comes to the cache, the web server will directly go to the DB, fetch the latest value, and update it into the cache. And this way, we will be able to resolve like 99.99% of the all of these race condition automatically, just because delete is idempotent. So it does not matter like delete is coming in which series. If delete is coming, the thing will be deleted. That's all. Even if you send 10 delete request to the caching server, it does not change the value. Like if you are sending 10 in a row, the value still gets deleted because it's not there. After the first request only, the value will be deleted, and the rest 9 will be just like the value is not here. There is one more interesting thing that I wanted to include in this discussion that many people might get doubtful. So wanted to clarify, what is Memcached versus Memcache? So these two, the one with a D versus a single Memcache system. Let's explain this in detail. Memcached is the original system that Facebook took. It was the open source version, and it's like a single server which is dumb, which is in memory. It's just a hash table. By dumb I mean, even if you are running two instances, so let's say if you have, let's say, instance 1, memcached server 1, and you have another one here, ms2, on a different port, so let's say this is 9000 and this is 9001, each of them will not know that there exists another server just beside them. So if they get the request and they don't have the answer, they will just say they don't have the answer. They will not say that, hey, you can look there. So they are dumb. Now, they are dumb, but they are very, very, very fast. And this is what we need in a cache. So there is no server to server coordination, like I said. But when we talk about Memcache, which is the distributed system of the same thing that Facebook built, the servers are still dumb. So all of these are still there. So let's say thousands of them. MS3, there is MS4. They are still dumb. They still don't know that there is just a server just beside them. But then you can think that then how is it different? It is different because now Facebook built a client, a intelligent client which knows everything on top of all of this. So this all are connected to this client. They call it MC router or router. Okay. We will talk about this again in detail when the time comes. So all of these entire system distributed one is memcache, and this individual system is memcached. Now, how does the client find the right server for a particular key? That is interesting. We will discuss this. Aggregation. So let's say if this server, this client is getting, let's say I want values for these 100 keys. What will it do? It knows that, hey, there are 30 keys over here, 25 over here, 5 of them are here, and let's say rest, whatever, are here. Now, instead of sending one request for every key, it will just create a batch request. Okay. So all of these 30 keys, batch request will be sent to this one, another one to this one, another one to this one, and another one to this one. And then it will aggregate all of these, and we will discuss this in detail. But there are benefits of this. Benefits because you will be able to get answers very quickly. You know where the answers are, and there is always network congestion that we will talk about, the UDP versus TCP, and that is also very interesting. The UDP versus TCP one, they have actually included this in the research paper also, that how using UDP will lead to faster query by around 20% something. I will discuss this again. So then there is replication and fault tolerance, because even though we have dumb server, we can create replication of those caching servers, so that if we want to, like, do further queries, we can just ask to the replication ones. Consistency is still important because we need to delete the data, but the thing is, now this client will handle which keys needs to be deleted across the server, and this way we are able to manage consistency as well. Before we dive deeper into the architecture and see what all things were done by Facebook engineers, there is something that we as senior software engineers often do, and that is finalizing that what will be the trade-offs. So there are often few things that we need to prioritize and few things that we need to let go of. There are few things that have been discussed in this paper as well, and let's just discuss them one by one. So first of all, the paper discusses that how Facebook engineers decided that they will focus on development which is only giving a real world impact. So by real world impact, what they mean was every optimization, it must solve a user facing or operational issue. They will not do just any development over Memcached just to show off their engineering skills. Everything should solve a user facing or operational issue. Now, this will save time because they will not jump into everything that might take time. The second thing that they decided was, and this is very important, stillness is a tunable parameter. What do you mean by this? The thing is, Facebook engineers are ready to give stale data to their user just to protect its backend DB. So, availability and performance are having much more priority than strong consistency. It's okay if we show the likes as 317 where the real likes is 318 or 330, but the data should be available in cache. There is a small chance of seeing old data, but that is better than having no data at all. So this is something that we should note, because in the upcoming discussion that we will be doing, this will come again and again, and you will observe this obviously. Okay, let's deep dive into this entire caching system, and let's start with a cluster, because at Facebook scale we are not talking about one server or two caching server. There will be thousands of these servers that will be inside a cluster. Now, the problem is that if there are 500 to 1000 clusters and the keys are distributed across all of these servers, if we get a query, I told you earlier that the paper mentions that for one single page load, they can get up to, like, it can take around thousands of like queries being done to the cache to just get the values. Now, if a single user request needs data from 100 of these different Memcached server, this will create a massive fan out, you know, problem. So you see, there is this all to all communication problem that is coming up, which will lead to querying across 500 keys. And now think what will happen if all 500 of them reply at the same point of time to the server. And this is for just one query. If we talk about hundreds of queries, thousands of queries at the same time, how much load the client can get. So all of these network congestion, in cost congestion problem of so many keys coming up together to the client can create a massive bottleneck, due to which cache miss will start happening. And what will happen if cache gives up that, hey, I am unable to perform? All of these queries will go to the DB. Now, so much of queries reaching directly to the DP will create such a workload that now my DB will also go down. And this is a thundering herd problem. So this thundering herd problem is going to take down the entire cluster along with it. And the engineering challenges that the team will face now is to maintain latency. They need to reduce it. So now they also need to maintain this entire network congestion. So this entire network congestion that need to handle, and accordingly now they also need to handle that all of these load from the cache miss should not reach out to DB. So these network congestion, these thundering herd problem, we all need to handle it, and we will see how it is getting being handled in Memcache. Let's discuss how Facebook will solve the massive fan out latency. Now, obviously, they cannot change the speed of light. So, there must be something that they must do within their entire architecture. So, they kept the system of a very smart client with dumb servers or simple server, you can say. So, smart client, simple server. And this ideology we will see again and again in this paper. Now, we will keep the server of Memcached simple and we'll put all the intelligence into the client. The client is basically the system. We called it the library of MC router or Mac router, and likewise. And it is acting as a proxy, and it is responsible for the all logic handling that we discussed previously, like which request should go where, how the error should be handled, how the request serialization and deserialization is happening, are we compressing the data or not, all of this. What is interesting is how they are doing it. So remember that graph class in the college where you were sleeping? There is a concept called as direct acyclic graph. If you have read about it, it is what is being used here. So what is being done? So let's say the entire process consists of various things, right? You need to like, let's say user data, then friends data, then let's say some other profile data. Everything is there that needs to be fetched. So there are hundred of queries that needs to be done. Using a directed acyclic graph, you can find the optimized path to fetch all of it in a minimum time. So, a directed acyclic graph will be created by the MC router or Mac router, and basically, according to it, it will batch those requests that hey, I know that these data reside in this particular server, so I will just batch all of these requests into one request and send it to the. This way we'll be able to bundle up more. We will be able to like uh, decrease the congestion that is happening earlier if we are just using one single key call to every server for these thousands of requests per page. Now, so this DAG will be used for the data independency, and it will help the client to fetch all the data concurrently. So if I know that I will need all of these data, I can just go to each source and take it at the same time instead of waiting in a series. Okay, first I will take this, then I will take this, then I will take this. I know which data is where, so I will take all of them all together, and then I will merge it on my side, and eventually these parallel requests are also batched, like I said. And in the paper, they have mentioned that on an average, 24 keys are being merged per request in Memcached. Batching and parallelism were great and huge wins, but Facebook team did even something great. They went to the layer 4 of transport layer of the OSI model. Now, if you were sleeping in your OSI class 2, then let me tell you there are 7 layers, and mostly like application layer, presentation layer, session layer, transport layer, then there is data link layer, and likewise there are 7 layers. TCP and UDP comes in layer 4 of the OSI, and let's talk more about it in the slide itself. During the testing phase, Facebook engineers find out that using UDP over TCP is giving them a 20% reduction in latency, which is huge. Although it was giving them a 0.25% of failures, because UDP is connectionless. So what is happening that you are sending GET request and just bombarding them to the server, and some of your packets might be dropped because there is no connection being made. But what you are seeing is, because there is no thing like as a handshake which is done in like TCP, so there is so much of fast behavior which is being seen in UDP. And as compared to that 0.25% of requests which are getting dropped, I think it's a win-win situation, because these requests can go directly to the DB and you will be able to serve your users faster, 20%, which is huge. So for read, Facebook went with UDP requests, but for write or update, they still went with the TCP. Why? Because TCP has this guarantee that if the operation is being done, it will ensure that it is being done. Because set and delete are basically state changes, so we need reliability, we need guarantee that the operation is being done successfully, and that is why TCP is a very good and better option to do this. And MC router or Mac router is basically used as a proxy to coalesce these TCP connections from the external clients, and internally these MC routers proxies are connected to the Memcached server. So they are also able to handle these many connection externally by offloading them to the MC router client, and only the cache is directly connected to MC router. Let's discuss that how Facebook tried to handle the third latency fix, which is controlling of in-cast congestion. The problem statement I told you earlier for in-cast congestion is, there are let's say the web server is trying to request 500 keys from 500 different servers, and all of them are trying to reply at the same time. So whatever here, this server will have a switch, right? So that switch will be overwhelmed by so many request response coming at the same point of time, and due to this, packets will start dropping. Now as the packets are being dropped, so client will see timeouts because it is not getting the answer for its query. So what will it will do? It will assume that there is a cache miss, and it will go directly to the DB. And then I explained that thundering herd problem, that if every request starts going to the DB will also fail. So how do we control that, how many requests we can do? So remember that class of DSA where you were being taught of sliding window algorithm, and if that class never happened, there is a problem only it could that you can try. And that particular technique is being used here as well. So there is a client side cache sliding window, which basically enforces that how, like how many requests the client can send basically to the server in flight at any point of time. And it's similar to, if you have read about TCP congestion control, if you have not, go read it, it's very interesting after this video, of course. But this is being done at the application layer. So when a reply comes in, if you don't know what application layer means, you also need to again study just that part that I was discussing in the previous slide, again the OSI model. So when continuing, so when a reply comes in, the request is sliding again. So now visualize this. So let's say there is this window which is limiting how many requests you can send to all of these servers. So if you make it very small, what will happen? The number of requests being sent will be very less, due to which the original number of requests which are in queue here waiting to be sent, the latency will increase, because now it is taking time for them to be processed. So the latency will increase. Now if you keep it normal, so then eventually you are trying to maintain the number of requests, right? But now what will happen if you make it so much bigger? Then you will allow every query to directly go and then come back to the router, and again this thing will again create the same thundering heart problem that we say. So we need to keep adjusting it, and this there is this figure in this research paper that is talking about it. So if they tried adjusting the window sizes, and they saw that what is the average latency in milliseconds that is happening. And if you will observe that the thing that I was telling you, that if they keep the window very small, latency is spiking. And same thing, if they make the window too large, the same thing happening, the latency is again spiking. But if they keep it in between, if you see 200, 300, 400, so window size will keep adjusting based on the number of requests. So if a response comes, window will become like +1. If a request is going, window will become like -1, and accordingly. And at a time of congestion, that if you are observing that there is so much congestion, you can just sync the window size automatically, and it will handle the congestion automatically as well. Let's talk about how Facebook managed to reduce the load which was being generated due to the cache misses. So we talked about this thundering herd problem, that let's say if a very hot item has been invalidated in the cache, so all these requests will start coming to the DB, right? So here is your DB, let's say, and now requests are coming from the cache directly, and these are not one but 10,000. So how will you handle it? Because it will overload the DB. So currently your DB was like, let's say, working for at a particular x rate, and suddenly it become 10x. So this is very interesting. Now solution for this is Memcached will give the first request the cache miss, that hey, the data is not present in the cache, so you can go and ask it from the DB. But it will also give them a 64-bit lease token. Lease token means only this request has the access to actually go to the database and ask that hey, what is the value. And when then this request will be fulfilled by the DB, it will come back and update the cache, and the other request, all these 9,999 requests, they will be told to wait, bro. So these all requests will be waiting, and this token is actually rate limited, like I said. So per 10 seconds, only one, for one key, one token will be generated. And this is the same thing that I was saying, that we can have a stale data, but we don't care. So only the client has access to go and fetch the data, and all these clients, all these 9,000 plus clients, are told to wait and retry, let's say, after some time. So they will be wait, they will see that someone else has already gone to go and fetch the data. So they will wait, and very soon the cache will be updated, and they will directly go and take it from the cache. And this way we will be able to solve the thundering herd problem using a leash. Leash concept is used at many other places as well, but this one is a very good example. There is one more thing, which is pools, which are basically like a partnering server for different workloads. We will talk this in detail again. There is one metric that is published in this research paper, which says just using this leasing technique, they were able to drop the request being made from 17,000 to 1,300 requests per second, and which is awesome, because you see now you are able to reduce the load by 90%, which is like tremendous. So there is also this concept of pool, which I will discuss in detail in the next slide. So let's go there. Okay, leases are fantastic thing for managing thundering herd, but what about workload interference? So there is, like you might be having an idea ki cache is there, so it will handle everything, but there is no like one thing fits all size problem or solution over here, because there are different kind of data. There could be a low churn data in the cache where the data is accessed frequently, but its value does not changes so much frequently, so it can stay in cache for long time, like say the subscriber count of my YouTube channel or my videos views. But there are data where data cannot live in a cache for the, like we cannot have stale data that much. So we need to keep in validating the data again and again, and then fetch the latest data. It could be like, let's say anything, something like live match is going on, there is a score which is there in the cache. So it can be anything. But the thing is key, these low churn versus high churn data, we cannot keep them at the same place. So Facebook has this pools made up of, so it has different pools for different kind of data. So these are isolated, as you can see, and there is like a wild card for everything. You can read more about this on the net. And there is also high churn versus low churn that I told you. So data which are being frequently accessed but not being changed that much, we can keep it here. And there is some data which is needs to be validated again, so it will have a very short TTL. We can place it them like here. Then we also have a cache miss cost. This is interesting. So suppose the example that I gave in the beginning of the video, that there is some popular machine learning query that is running since 1 day, and you need to store it somewhere in the cache so that it does not, like, gets deleted. But the thing is, again, do we need to delete it? Because even if this data is not being accessed that much frequently, but if we delete it, then the operation or the cost that will be done to get back this data is so huge that we say that, hey, I want to give this data no matter what. So again, we can have a different pool for data like this, and we can store it here. So these are different use cases. So this way we can actually reduce the load for different kind of data. And there is now replication angle as well. So let's say we have some very hot data sets. There is a particular key, and due to this, we can actually replicate these small and very hot data sets, and this will result in handling the high request rate, or we call this multi-get. So due to this, we will be able to reduce the load per server, because if we are having two copies of a particular server, we will be able to handle more queries in a better way. And although we are provisioning a replication, but due to this, we need more memory. So we are now using twice the memory for the same data, for a better latency and better load distribution. Okay, so till now we have discussed how Facebook engineers worked on optimizing the latency and the load. But what about failures? Because as backend engineers, if I'm designing a system consisting of thousands of fleets of server, we won't talk about how we will act if the failures happen. We should discuss how we will act when the failure will happen, because failures keep happening. Server dies due to various reasons. We will always have server failures due to power failure, network partitions went wrong, or there was a kernel went rogue, some kind of issue. So we have to design for all of these scenario, otherwise our design will be very brittle. So one failure can lead to a cascading effect of failure, and let me explain you why. Let's talk about this example or scenario where basically there is one Memcached server which is only handling, let's say, 1/1000 of your entire caching fleet. But your DB is designed to handle only 2% of cache miss. And now, when this server failed, what will happen? Because we are working on a look aside caching system, all of these requests will start going to the DB. And suddenly your DB request starts piling up, starts going up. So the number of requests that were actually being made is now 10x or 100x. And DB starts getting overused, and all of these start things piling up. DB might choke. So you see that this one single isolated server can take your entire DB down. Now, any beginner will think that, okay, I will just rehash the entire, the cache memory into the other 999 servers of cache that we have. And the paper specifically says that this is a very terrible idea. And let me tell you why. So suppose there is a very hotkey. Okay, there is one specific or two specific hotkey that is being continuously fetched from a caching server. Now, when you will distribute it among the other healthy servers, what will happen? That queries will keep coming for that particular hotkey, and now what will happen? It will take the other cache down, and again, due to because another cache is down, again more calls will start going on to the DB, and then what you will eventually see is a cascading effect of, due to one or two key, the entire fleet of cache are getting impacted, and latency is increasing in the DB. So what is a good way to handle this? The Facebook team came up with this concept of gutter pool, where basically they reserved 1% of the entire cache capacity to a separate, which is just sitting idle. Okay, now let me show you. So suppose this is your actual caching system. Now 1% of it, like just to show you some significance, I've kept it a little bigger, but let's say this is 1% and this is 99% and this is 1%, and here is your DB. Now, the thing is that here will be your client setting. So the client logic is changed in such a way that first of all, the client will go to the actual cache. Now, once it reaches the target server, it will see that, hey, the request has timed out. So it will assume that the server has failed. Now, it will go to the gutter pool and it will say, hey, I want like value for this. And again, if it is a cache miss, then DB will be asked the value, and then accordingly it will be stored in the gutter pool. And likewise, from now on, if it is actually a hotkey, the TTL here is very less. TTL is very less in this gutter pool. So it act as a shock absorber, because now you will be able to like withhold those hotkeys reaching out directly to the cache. And this way, meanwhile, the background workers will start spinning up a new server to replace the one, or maybe fix whatever is going on with some faulty server. So you see, this way you are not only able to protect the database, you are also able to protect the healthy caching servers, and as well as give a little bit of protection to the DB as well. All right, so till now we have mastered the art of scaling within a single large cluster. Now we can handle what all things. So we can handle latency, we can handle load, we can also handle failures now. But what can we do now to optimize more bottlenecks? And the next level of scaling should be basically making clusters of server run within a single place, or let's say data center. These collection of clusters is what is called reason by Facebook. Now here becomes things interesting, because now you are having multiple clusters, basically the Memcached client and the web client, and all of them are connected to one single storage layer, or let's say master DB, and everyone is getting data from that DB only. But there are different clusters. Now this distributed system brings problems of new kind, and I will explain you what will happen now. Suppose there are three clusters. So let's say A, B, and C. So we have A here, we have B here, and we have C here. And each of these has, let's say, there is one master DB. So we have master DB here. Now A, B, and C, there is one write that is happening via A to the DB, but B and C are also having their own cache, right? So let's say B is having cache, C is having cache, A is also having cache. Now if A updates something in DB, it can invalidate its own cache, that hey, delete this. But what about B and C? because it's not the duty of A to do it, because like I said, Memcached is dumb. It does not know there is another client just beside him. So what will we do now? Now, looking from an overall level, someone can say, hey, let's just tell A where are B and C, and it will just send out a message to B and C that you can delete your copy of, let's say, this key K that it has deleted from your cache as well. But you see, the paper itself says it's a very wrong thing to do, because what if A dies just after clearing its cache? And this also is creating a fan out problem again, because now every server has to talk to every server, and we want to avoid this at all cost. So there, Facebook implemented another invalidation pipeline layer, which they called mcsqueal something, or mcsqueal. So now let me explain you how it works. So every commit that is being done, so let's say there is an update operation being done by A, so it will eventually go to the DB. Now while this write is being done, what will happen that what all keys needs to be has been updated or needs to be deleted from the cache, these all data will be stored in the cache log. We call this the commit log basically. And there is an analytical engine which is mcsqueal. It will go through the entire commit log. It will find out that okay, so this key needs to be removed or deleted from all of these like server, and it will now start sending these data to our mac router or mc router basically. Now mac router will identify that okay, these keys are where, like the replication ones or the duplicate ones, and accordingly it will send all of these delete requests to the actual places where these are needed. Now you will again think, why is this needed and what benefits it is giving us? And let me tell you, it is very beneficial. The first benefit is, of course, we are invalidating now only once it is committed in the DB. So we can say it's a source of truth. And apart from that, now because we are having access to so many delete requests, we can actually again use the batching concept that we discussed in the UDP and TCP section, that we can now batch delete request as well. And the paper specifically talks about is that using just this technique of batching delete operation, they were able to speed up this process 18 times, which is huge. The entire delete process was able to speed up just because of batching. And this is so beautiful. This way, we are not only able to decrease the network congestion, but we are also able to decouple and make it a highly efficient distributed invalidation pipeline. On page 7 of the research paper, Facebook talks about how they build a regional pool. And let me explain you the first problem statement first. So let's say there are 10 different clusters. So let's say C1, C2, C3, and likewise C10. Now, all of these clusters are deployed in various regions, right? So let's say I have a user 1 here, which is closer to C1. So it can directly fetch the data from C1 because it will give the least latency. That is why we designed Memcached, right? To reduce the latency and give user data very fast without affecting the DB. So yes, everything is getting fulfilled. But now, do we need to store the same data everywhere? Yes, we can surely do it. But do we need to do it with every data that we have? I mean, there must be some data which is good to have on cache, but we don't need it on every caching system because it is taking a lot of space. So if you are having 10 caching clusters, you are like that single file is taking 10 times its original size. And this is where regional pool came. Uh, Facebook decided to make a regional cluster, let's say RC, and this will hold all of these cold data which needs to be stored in cache, but we don't need to store it on every cache. Now once we have decided that okay, even if this user is nearest to C1, I want user to go and fetch data from RC. So being a backend engineer, what do you think we gave up here? Think latency. Facebook decision to give users extra latency just to give them this caching layer is might seem like a well consciously made deliberate trade-off, because now you see what is happening that uh, now the users need to like do an extra network hop and bring that data from some other faraway cache, but Facebook is able to save terabytes of RAM by saving these cold pieces on one single cluster, and it can save extra memory for other hot items. So we will discuss this again in the last section where I will show you the graph for this. Let's talk about one more interesting case of what will happen when we try to, there is a new cold cluster getting just started. By cold cluster, I mean, so let's say there are hundreds of servers, right? So let's say there are so many servers there, and suddenly you just added a new fresh server which has no memory at all. Now, your DB, let's say it is here, right? So your DB is here. And now what you will see is now your client might be reaching out to various of these for different keys. But if it reaches to this cold cluster, which is actually empty, what will happen that it will again go to the DB directly because there is cache miss. Now, if lot of calls starts coming to this cold cluster, what will happen? So eventually everything will be a cache miss, and then again the load will start going up to the cache. So it's a thundering herd problem again. And now this will again lead to DB getting choked, latency spiking, and we don't want that. So how can we handle this? Let me explain you the solution with a better diagram. So let's say all of these red ones are actually hot cluster of cache, and we have just started a new cold cluster over here. Now, what we will do is whenever this cache will get a query, it will go and first look into the hot cache, whether the data is present over there or not. And now what will happen that if data is over there, it will just copy it and return back, or else it will go to the DB and get the data. It sounds good, but again it has one more problem, that what if the data that is being copied from the hot cluster is actually meant to be deleted. So let's say there is mcsqueal over here, it sends a delete for the data, but the data is being copied here and it reaches here that hey, delete the data. Now our cold cluster will hold the stale data forever. Now how we will resolve this? The fix for this is again simple and very clever, a concept called as hold off deletes. So basically mcsqueal over here, what it will do that whenever it receives a delete command over here, then while sending it to the cold cluster, it will tell the cold cluster, hey, delete the data and also hold off any update or addition of this key for next 2 seconds. So in this duration, if the client will come over here and try to find out, hey, is there a data over here in this cache, then this cold cluster will go to the hot cluster, but as it is marked as like not to add, so it will not be added. The client will see that okay, there was a cache miss, so basically client will directly go to the master DB itself and fetch the data, and then accordingly the updated value will be updated in the cold cluster. So it's just putting over there delay of 2 second or 3 second, and I will show you the graph later on also, that how much time it takes for all the deletes to reach to the server. That graph is there in the research paper, and you will see that this will solve almost 90 to 99% of the problems. So far we have scaled a server, let's say, and this server, we have then let's say a cluster of these servers, and these clusters together, they let's say form a region within a single data center. Okay, now this region, which is actually a cluster of servers, is scattered across the entire globe. So we can have, let's say, US, then we have Europe, and likewise we can have multiple of these regions scattered all across. And again the distributed problems comes that now, because there was a master db inside one region, now what we will do for different regions. So let's say if a person is sitting here in US and a client is another in Europe, now we cannot have just one master db and then we expect that every server around the globe will call directly just one master db, because the latency will be too high. So the architecture again must change here to solve this distributed problem, and this is what is happening. So eventually what happens that there is one master database in a particular master region. So let's say if US is the master region, so this will contain the master DB, and all other regions, Europe, India, Asia, or whatever, each of these will have just a replica of the master DB. Now, the clients in the US will directly call the master of US, but the Europe clients will call the master DB replica in their own region, and this will solve the latency problem by a huge gap. But it brings the same problem again, that now data can be stale. Let me show you an example what I meant. So basically user writes to the master db here, and now what happened that the delete of this key eventually will happen here instantly. But this, because it's just one call, like delete key, so delete will reach to Europe very much faster than the updated value that will reach here eventually the master db. So this will reach much faster, so the cache will be clean, and the actual updated value will come much later from the master db. So whenever a client will ask for a particular value of this key, let's say k, so what will happen, the cache will be empty here. Now it will be fetched from the replica of the db at that point of time, but this data is stale because the value has been updated in the master db, but it has not reflected in the slave db basically, or the replica db. So how can we handle this now? Let's understand this problem a bit deeper before we go into the solution, which is actually remote markers. So basically we have two dbs, one is a master, one is a replica. Now there has been some update in the master db and it needs to reach to replica, but before it's reached to replica there is some cache of this, okay, and some cache of this, let's say a master cache, and there is a replica cache. Replica cache is directly fetching it from here, so it is getting stale data. The solution for this mechanism is actually a remote markers. So this is clever but a bit heavy, so let me explain you how data is being synchronized basically between two different data centers. Let's trace the right path again, but for a user who is inside a replica region and wants to write to the master region. So what will happen first, the web server will first set a tiny remote marker, let's call it r_k in the master region cache. Okay, so this is a cross country write. This marker basically acts a flag that it say, hey, a write is in way for the key k. Okay, then it sends the actual update to the master db. So the master db is now getting the request to update the value of key k, and it also contains detail about invalidating the k and the r_k, basically the remote marker. How it will do it, that is included in the SQL statement itself. Now what will happen that first of all, though, it will immediately delete the key k from its local cache. Now the read path, this time a user in replica region will get a miss for the key k in the local cache. Now after getting the miss, it will not go to the replica db, but instead it will first go and check if there is a remote marker in the master db. And beware that this is a cross country call, So yes, there will be latency, but now when it will reach the master DB, it will see that, oh, there is a marker placed. So this means that there is some data coming up to the local replica of master DB, and that has not been done yet. So the data needs to be fetched directly from the master DB, not from the replica DB, to avoid getting stale data. And this is how we will be able to resolve this distributed problem of getting stale data in the cache. What would have happened if the user went to the master DB and there was no remote marker? So obviously that means that the local DB replica is in total sync for that value from the master DB. So it is safer to read directly from local rather than going global. And this way they will be able to get always the correct value, and this will add latency, but this is basically the price we have to pay for getting correct data. All right, so far we have treated Memcached server itself like a black box. But the thing is, when we are operating at a scale, so we need to go deeper inside it and, like look into what all things are being done there. And eventually, Facebook team did the deep dive into this open source and find out what all are the bottlenecks. The research paper talks about how Facebook team went and did a deep dive on the code of the open source program and made few contributions back as well. And there were few things that they kept to themselves, like locally to Facebook internal use case. So we will discuss this in detail. So first of all, the open source version, Memcached, basically, it was single threaded, and this was a major bottleneck. Eventually, the community did make it multi-threaded, but again, the problem was there was single global lock. So even if you have, let's say, 16 core CPU or 12 core something, but the problem is there is one global lock, so it was not that much performant. So Facebook team managed to build a more granular lock system. In the research paper, Facebook team gave this graph which showed just by implementing this granular lock, they were able to bring the peak throughput on cache hits from around 6 lakh to 18 lakh per second, which is like 3x improvement, which is huge. Now, there is another graph regarding TCP versus UDP that we have been discussing over all of these videos. So that we discussed, so UDP is faster than TCP for gets. There is a miss of around 0.25%, but we are ready to let it go because we are getting so much faster, decreased latency, that 0.25% directly going to the DB won't be that much of an issue for us. Multi-gates, this is also mentioned. So Facebook showed that by using multi-gates, so like basically batching the gate request together, they saw that a 10 key gate, so making 10 calls for a single key versus making one single call for 10 key is 4 times faster than the previous version. So by just batching a request, you can get up to 4 times faster speed. There are some other improvement as mentioned as well, like auto expanding hash table, basically, which helps reduce the time complexity again to big O of 1 rather than making it big O of n, because at huge scale the hash table eventually needs to be increased once it reaches a certain threshold. There is also a discussion of they gave each UDP port its own thread, and that also helped it, making it faster. You can think about it in detail again after the end of this video, that why did this happen, and post it in comment as well. The next optimization that we are going to talk about is really cool, that how are you actually going to manage the entire memory. So you cannot just free up after every delete the memory basically using malloc or calloc, if you have uh, read about C programming language. So Facebook did it with the help of concept of slabs. I will explain it further. So Memcached created a slab allocator, which at the run of startup used to create different chunks of 1 MB each. So there are different chunks. Now each chunk used to have a pre-allocated fixed size. So let's say there is 164 byte class, there is 72 byte, there is 180 byte. Now whatever item will come, it will have some size, right? So it will find the best class that can fit it properly. So if there is something like 66 byte, it will go into the 72. So an item came, it came here. Then again, some 67 came, it will come here. And likewise, so for different slab allocator classes, the thing will start going up. But then again, a problem came that the workload. So let's say this 72 byte or this 64 byte has different number of items, right? And this has different number of items. This has only one item, let's say. So this 64 byte of slab might be full, and then it starts evicting the old ones. But the thing is, it's being done at such a high speed that even most recent items are getting evicted. So how will we handle this? Because this 80 bytes class is actually sitting idle and just sitting over there and it's doing nothing, whereas another one is so hot that it is evicting keys very fast. To fix this, Facebook built a adaptive slab allocator, which what it does, it this is basically a background thread which constantly monitor each of these slabs eviction rates, and also the age of items that are being evicted from every slab class. Eventually what will happen that it will identify the needy classes that are evicting hot recently used items, and then it finds the donor class. Once this adaptive slab allocator finds something nahi, once this adaptive slab allocator finds a match, what it will do, it will take an entire 1 MB of slot, basically slab from the donor class. So this will become the donor, and then it will evict all of its cold item and then transfer this 1 MB back to this one. And all of these being done are dynamically basically resizing the entire memory, and this is also being done at the runtime only. So this will help us the eviction policy to be handled properly for this hot item of 64 bytes. And the goal is basically to balance the age of oldest items. So if it is evicting in, let's say, 5 minutes, this should be doing in similar somehow. It should not be that one is evicting in 5 seconds and another one is evicting in 5 minutes. So now we are towards the end of the research paper, and there are two more features that Facebook talked about. First is the transient item cache, and another one is how they handle software upgrades. So let's discuss them in very short overview. But they are awesome concept to know. So first of all, let's talk about transient item cache. So let's suppose there are various items which are actually short lived. Let's say within 5 seconds, it should be there is a TTL of 5 seconds. So the value is of no use after 5 seconds. We need to fetch new value. But the thing is ki when we say TTL of 5 seconds, it's not like after 5 seconds it will be deleted. It will be basically expired, marked as expired, that hey, this data is not active that much anymore, so we cannot use it. But still, all these short-lived items with very short TTL are still there in the memory. So these are wasting spaces, and the LRU policy will evict them, but we don't know when. Eventually the garbage collector will run and it will clean it, but it can be like within 15 minutes, within 10 minutes, or within hours. We don't know. So in order to just remove these extremely short-lived items, Facebook built this feature of transient item cache, where what they did is a hybrid policy of a circular buffer of linked list, and it has the index as the TTL, basically how much time it has to live in the memory, basically the way of expiry. Now the thing is, there will be one single thread whose work is that every second it will go and it will find out that how many items have expired in this last second. So let's say at t is equal to 0, this marker is here. Now we know at t is equal to 1 these two have expired, so it will just go and evict all of them from the memory, and this way it will keep running for the entire circular linked list until new items keeps get added, and older ones are getting removed again and again and again. But the metric that Facebook put regarding this in the research paper was using this. So this short-lived item used to take around 6% of the entire RAM, they were able to bring it down to 0.3%, which is like 95% of reduction in memory wastage. So you see, we are talking about petabytes of data. So at this scale, this thing is huge. So you can think about how much saving this one technique, one method had done for Facebook. Another interesting improvement that Facebook did was how they used to handle software upgrades. So, see, Facebook had this concept of cold and hot cluster, right? We discussed this, but eventually, what will happen that in order to warm a cluster, it takes time. Let's say 12 hours, which is huge. But if we want to upgrade, let's say a caching client, so I had told you that it is dumb enough. So all the data will go, like it will evict, and now we cannot take risk of evicting every cache one by one. So this way the deployment will take forever. So what they did, in just case of deployment, they used system v memory. System v memory, if you have not read like the operating system fund, this is concept from that operating system. So it's basically a very fast memory where there is no copying required. Everything is being shared between different processes, which does not need to be child processes. You can read about it more in detail, or I will create some video regarding this. It's very interesting concept, like how to copy so much fast that does not look like copy at all. But that thing we will discuss in some other video. But the thing is that Facebook used system v memory, so it used to store the data in system v memory, and it will update the client, and eventually what will happen that once the update is done, it will again go there and fetch it back from the system vc'd memory, and this way they were able to reduce it to, let's say, 30 minute or 1 hour to of deployment. It's like instantaneously they were able to rule out deployments for in the entire fleet of clusters that they had. Around page 11 of the research paper, the team has published a lot of graphs and metrics. Few of them I will be discussing on this slide, what they mean. And let's first start with these are very informative, and whatever you have discussed till now, these metrics will show you that what we were discussing was actually like correct. So first of all, the fan out problem that we were discussing. So if you look at this graph particularly, you will see that a popular data intensive like request or a data intensive page will trigger how many like queries to how many server. So if you will see here, you will see that these are the trend for a data intensive page, and you will see that even at the 50%, we are going to ask for around 200 servers for the data. And as you move up, this is like very less for like the smaller request. You will see that for the 50%, we just hardly need to reach to 20 server. But as we go up, we will basically see that data intensive pages are going to call hundreds of distinct servers that we were discussing since beginning. Another thing that you will see in this graph is the thing that we were discussing, that there is various large item as well as huge like smaller items as well, and this graph shows basically that the same thing, that percentile of request, how much data they need. So if you will see here, you will see that there is a huge variance, because if you see the median, it is somewhere around 135 bytes as mentioned in the research paper. And if you talk about the mean, then that is somewhere around like 900 yes, 954 bytes. So this proves that there are very huge items, and there is nothing common like what kind of data is being come. And we discussed this at the initial of the video, that there is a heterogeneous type of media that is being asked, and there is no like a simple pattern. There is one more thing for invalidation latency, this third graph, then we will come to the pool statistics. So there is a table again that is regarding like this pool statistics, but it is in the research paper. You can refer to that in the like I will attach the link of my personal copy in the description of this video. And you can see that the invalidation latency, because like 99.99% of the delete request, basically the invalidation request, were successful within 1 second, which is awesome. And if we talk about the master region, and for the replica region, this was slower. It used to take a lot of time as compared to the master region, and this proves the hypothesis that we were discussing, that the replication lag, it will happen if we are going for a delete in a replication, replica db. So these are the data that is over there, and there is one more table that I was discussing. So if you go through that table, you will see that basically the concept of pool architecture that we were saying. So basically it will show you that for smaller items, let's say 66 bytes, there is a massive hit rate of around 710 k per second, which is, like how much it means. If we talk about the regional pools, which are huge items but like not that much active, so they hardly get of 9k per second. So you will see why we were focusing so much on keeping this kind of data in regional pools as compared to replicating it across different clusters. All right, we have discovered a huge covers of concept today in this video, and just wanted to summarize once everything before closing the video. So first of all, we talked about the core concept that Facebook is using of look aside cache. So if we miss the request, then we will go to the DB, and accordingly the data will be updated in cache, and likewise. We then talked about how within the cluster we are able to optimize latency or the load basically with fan out problems and smart clients. We are using batching, we are using UDP for get, we are using sliding windows so that there is like breachment of number of calls being made by a client is not done that much. Then we talked about thundering hertz, we talked about the concept of lease. Then we talked about in-region replication, how we are handling it with the MC mcsqueal or mcsqueal pipeline, how we are validated with regional pools ka concept. And then we talked about how we are doing it across regions, basically the consistency problem via the solving of replication lag by putting remote markers over there. Then we finally discussed the core trade-off of availability, basically performance and ability that we initially discussed in the beginning as well. That these are the design principle that Facebook engineers took. That they believe that they should focus on availability and performance, and rather than giving strong consistency, like the value should be always latest. So you will see these trade-offs in the entire design of this research paper, and this entire system basically is built on the willingness to serve slightly stale data to basically prevent the catastrophe of all these requests reaching directly to DB and making a thundering herd problem. So that is all that will be covered in this video on this research paper. It was an absolute treat to go through all of these concepts and understand how large scale distributed system caching actually works at such a huge scale. And I hope my effort of creating this video would have certainly helped you a little bit understanding these concepts. And I will really appreciate like if you could like give me some feedbacks, or maybe I don't know, like within the next 1 year I hope I get like around 500 likes and somehow a good number of subscriber as well. So that is all from this video. Do check out this my own copy of this research paper. I have done proper highlighting thing while I was going through it. And uh, I will see you in some other video of break the tech then. All right, bye.